This video is to help you understand Gershgorin's theorem. I'm going to presume you've already looked at exploration 1 and you've changed some of the entries of this 3x3 matrix and seen what it does to the circles and tried to answer some of the questions. So we're going to begin by helping you understand the statement of Gershgorin's theorem. The conclusion of the theorem is that the eigenvalues of A are contained in the Gershgorin region gamma of A. That's a capital gamma, which is the Greek G. And it's defined in the equation right above it. It says that gamma of A is defined to be the union of the gamma I of A's. Now these gamma I's are Gershgorin disks. And it says the union as I ranges from 1 to n. So there are going to be n disks if you have an n by n matrix. So in the exploration, you had a 3x3 matrix, and you saw 3 disks. And the eigenvalues always appear in those disks. I guess the only other thing is this equation 1 here. What is this? So I'm going quickly to the appendix, section 12.2, scroll past the first few examples and properties down to equation 1 of this module, and I want to focus on it for just a moment. Let's write down equation 1 from the Gershgorin module, the section on Gershgorin's theorem. So that one said absolute value of z minus AII is less than or equal to RI of A. And so if you think about what's going on here, it says above, or right below equation 1 from the complex numbers appendix module, we have a complex distance formula. If you have 2 complex numbers, the distance between them is z1 and z2. Now in our equation here, let me just point out that z, that's a variable. So that can be lots of different complex numbers. Now the other number, AII, that's some number in the matrix, in the diagonal, because the row and column are the same. So suppose you have a matrix and I don't know, your middle number A22 is 5 or something like that. So I want to think about what would this say? This says the distance between a variable and 5. And suppose I knew that it was equal to 1. Well then, of course, in complex numbers, you have the real number line, which I'm used to, and the imaginary number line I'm not so used to. But here's 5. And if I say, well, give me some numbers that are 1 away from that, well, I think I'll switch colors to red. And I know that 6 is 1 away from 5, and so is 4. But you can also go up or down 1 because this is the number I. So this would be 5 plus I, and down here would be 5 minus I. And actually, if you were to graph all the numbers so that the distance equals 1, well, from geometry class, you know that's a circle, right? But that's not what our equation 1 says. Our equation 1 on the other page says we want z minus AII to be less than or equal to that number. And so let's imagine what it would look like if it was less than or equal to 1. Well, I guess the difference is that anything in here has a distance less than or equal to 1. And so it's not just a circle, but it's a disk. And that's the point of equation 1 on the other page. Let's go back to it. This says how to define the ith disk, right? So if I wanted the second disk, gamma 2 of A, well, it says it's the set of complex numbers, z in the complex numbers, such that, and now it says the absolute value of z minus A22 is less than or equal to R2 of A. All right, and I'll explain what that is. And so I guess the centers of the disks are the diagonal entries. And we'll see this in example 1 in just a second. Now, what about the radii of the disks? the radii are these absolute deleted row sums. So what is R2 of A? R2 of A is a sum. It's a sum of certain entries. These entries would be A row 2, because I is 2, and then whatever J is. Now J can be anything except I. So basically, R2 of A would be A row 2 column 1 plus A row 2 column 3, except that you want to take the absolute values of those things. And so we'll see how this all works now in this next example. So it asks me to plot the eigenvalues and the Gershgorin region of each of the following matrices. I'll start with matrix A. And so we're going to plot gamma 1 of A in blue. And so if I look at row 1, well, this 1 right here, that's the center. And so there is a center of the disk at 1. And the radius of the first disk is also 1. And so my Gershgorin disk is a circle of radius 1 centered at 1. That's not too hard. Let me get a different color for gamma 2. Why don't we use red? And so for gamma 2 of A, well, again, it's the diagonal entry. So that's the center of the second circle. And so it'd be centered at 0, which is right there. Remember that these are complex numbers. So example B will show that a little bit. And the radius is the absolute value of everything else. So there's a 2. So we want a circle of radius 2 around 0. And so I guess it would look something like this. Okay. Now I didn't compute the eigenvalues yet of this matrix, although it's pretty easy to do, right? So if I wanted to take the characteristic polynomial, I would take the determinant of the matrix 1 minus lambda, 1, 2, and 0 minus lambda, right? Because this is going to give me the characteristic polynomial. Negative lambda times that gives me lambda squared minus lambda, and then I need to subtract the 2. And so this factors pretty nicely. It's lambda minus 2 times lambda plus 1. And so that tells me that the eigenvalues, which I haven't plotted yet, but I'm supposed to, are positive 2 and negative 1. And notice positive 2 is right here on the boundary of the two disks, and negative 1 is in the red disk. What the theorem says is that the two eigenvalues will be in the union of these disks. In this case, the blue disk is totally inside the red disk. So basically what I know from the theorem is that the eigenvalues have to be somewhere in this red disk. And it turns out that this is where they are. For part B, we want to find the Gershgorin region of matrix B. And this is going to be the union of 4 disks because, so we'll say I equals 1 to 4 because n equals 4. There are 4 rows. Each row gives us a disk. And the disks we can write as gamma I of B in this case, matrix B. And so we'll talk about each one. So gamma 1 of B, right? Well, basically what we need to know is that each gamma I of B satisfies Z minus BII. So that's the, and put that in absolute values. That has to be less than or equal to Ri of B. So that's the lowercase b is the diagonal entry of matrix B. That's the center of the circle. So for gamma 1 of B, let's look at row 1. And we need to plot 1 plus I. And again, this is the real axis and this is the imaginary axis. So when we plot 1 plus I, we go to the point 1 comma 1. And that's going to be the center of gamma 1 of B. So what we need to know, I guess, is the radius, R1 of B. Well, what that equals is the absolute value of the entries in row 1 that are not on the diagonal. So it's the absolute value of 1 plus the absolute value of I plus the absolute value of 0. So I know you know that this is 0, and I know you know that this is 1. Do you know the absolute value of I? Well, it's 1. And the reason is because absolute value means distance. And so the distance that I is from 0 is 1 because it's along the imaginary axis, right? And so this radius is 2. R1 of B is 2. And so what that says is we draw the circle centered at 1 plus I, which I already put down here, with radius 2. And so that would be this circle. And so it's going to contain some of the eigenvalues, perhaps. Well, there's 3 more disks. The union of the 4 disks will contain those eigenvalues. Actually, we can plot the eigenvalues right now. Let's do that. I'll plot them in red because when you have an upper triangular matrix, then we know that the eigenvalues appear right on the diagonal. And so 1 plus I, the center of this disk, is actually an eigenvalue. Actually, in this problem, the eigenvalues are the centers of the disks. Now, that's not always the case, of course, but 4 is an eigenvalue. 2 is an eigenvalue. That's also in this disk. And -1 is an eigenvalue over here. Okay. And so, yeah, we're getting somewhere now. So let's talk about the second Gershgorin disk, gamma 2 of B. I'll plot it in red. What's the center? Well, the center is 4, as we said earlier. That's the center of this disk. What's the radius? Well, R2 of B, the radius would be, well, if you look, we have in the row 2, we have a couple of zeros and we have a 1 plus I. So we need the absolute value of 1 plus I. So how far is that 1 plus I from 0? You know, I guess it's this distance you're thinking about. That distance you probably know if you know how to find the diagonal of a square. But if you don't know, there's a nice formula for, and this comes from complex numbers. Usually we use z for complex numbers, right? But what you do is, if you have z, what you can do is you can get its absolute value by taking the square root of z times z bar, which means the conjugate of z. And again, you may have never done this before, so I'll show you how to do it. If I take 1 plus I and I want its conjugate, what I do is just change the sign of the imaginary part, so it's 1 minus I. And one cool thing about multiplying a complex number by its conjugate is that you get a real number. You won't have anything imaginary anymore. I mean, think about FOIL. 1 times 1 is 1. 1 times negative I is negative I, but then when you do the inner, you get positive I, so those go away. So the last thing we get is we just get minus I squared. But you probably know that I squared is -1. So what we really get is the square root of 1 plus 1, which is the square root of 2, which again, you could have gotten that with geometry. So square root of 2 is approximately 1.41, okay? So my circle number 2, gamma 2 of B, is centered at 4, as I said earlier, and its radius is a little more than 1.41, and so I guess it would look something like this. Oops. A little more than 1.41 would look something like that. Okay. We have 2 more circles to plot. Let's go to black, and we'll plot gamma 3 of B. Now gamma 3 of B is centered at 2, and its radius, R3 of B, would be, well, we have a 0, and a -1, so the absolute value of -1 is 1. So this Gershgorin disk is a circle of radius 1. So I guess it'd go right through that 3 there. The last one is interesting. What about R4 of B? The center of the 4th disk is -1. So that eigenvalue, -1, the Gershgorin disk has radius 0. So it's just the eigenvalue itself, if that makes sense. So this is a picture of the Gershgorin region of matrix